Have you ever noticed how time seems to stretch when you're waiting in line, but disappears when you're having fun? What if I told you that time isn't as fixed as your clock suggests? Welcome to Science for Sleep, where tonight we're unraveling the mystery of time itself. From Einstein's mind-bending theories to why childhood summers felt endless, we'll explore how your brain warps time in ways you never imagined. Get comfortable, relax, and let's drift into the fascinating illusion of time together. Your brain's time warp. That moment, staring at the clock in a waiting room, watching the second hand crawl. While hours vanish when you're lost in a good book. This isn't just your imagination playing tricks. Your brain actually processes time differently, depending on what you're doing. Neuroscientists have found that our perception of time stretches and compresses based on our attention and emotions. When you're bored or anxious, your brain constantly checks the time, creating more conscious moments that feel longer. Every glance at the clock creates a new memory marker, making waiting seem to last forever. But during enjoyable activities, your brain stops time checking. Hours can pass without forming many distinct memories, so they seem to disappear when you look back. Children experience this most dramatically. Recall how summer vacations felt endless when you were young. That's because everything was new. Your brain was constantly forming fresh memories and learning patterns. First bike ride, first sleepaway camp, first crush. Each day was packed with novel experiences that created dense memory formation. As we age and routines settle in, familiar days blend together, with fewer distinctive moments to mark the passage of time. Researchers at University College London found an interesting pattern. They had participants estimate time durations while doing different tasks. During engaging activities, people underestimated elapsed time by up to 30%. In boring conditions, they overestimated by nearly the same margin. Your brain isn't lying, it's just recording events differently based on how much attention they require. This explains why time seems to accelerate as we get older. At age 5, 1 year is 20% of your life experience. At 50, it's just 2%. Childhood years contain more firsts that stand out in memory, while adult years often blend routine events that leave fewer distinctive marks. Some psychologists suggest keeping novelty in your life, trying new foods, traveling unfamiliar routes, learning skills to slow this subjective time compression. Emotions warp time perception too. Fear literally makes time feel longer. In dangerous situations, your brain records memories in slow motion to help process threats. People report car crashes feeling like they lasted minutes rather than seconds. Positive emotions have the opposite effect. When you're laughing with friends, evenings vanish faster than empty ones. Your body's internal clocks complicate things further. Circadian rhythms make afternoon hours feel quicker than early morning ones. Temperature affects time perception. Warmer environments seem to pass faster than cold ones. Even your metabolism plays a role. Athletes often report time slowing during intense focus, while fatigue can make hours drag. Culture shapes these perceptions from childhood. Western societies typically see time as linear, past to present to future. Some indigenous cultures view time as cyclical, like seasons repeating. These foundational concepts influence how we experience duration throughout life. A child raised with agricultural rhythms may feel time differently than one surrounded by digital clocks. Language reflects these differences too. English speakers metaphorically place the future ahead and past behind. Some languages reverse this. The Aymara people of South America gesture behind themselves when speaking of the future. Their word for tomorrow literally means the day behind us. Such linguistic structures shape how speakers conceptualize time's flow. Modern technology heightens these effects. Digital clocks train us to see time in precise increments, unlike sundials that showed gradual movement. Constant notifications fracture our attention, making some days feel both rushed and interminable. Many people report pandemic lockdowns distorting time perception, lacking normal routines and social markers. Days blurred together while months somehow flew by. Interestingly, memory recall follows similar patterns. When reconstructing past events, your brain doesn't replay them like a video. It reassembles key details based on how they were originally encoded. Highly emotional or novel moments get stored with more contextual cues, making them feel more recent when recalled. Routine events merge together with fewer distinguishing features. Some psychologists suggest keeping time journals to counteract this compression. Briefly noting distinctive events each day creates more memory markers. Over years, this can make periods feel more fully lived, rather than disappearing into haze. Others recommend periodically changing routines, taking different routes to work, or rearranging furniture to stimulate memory formation. Your brain's time-warping abilities actually serve important functions. Anticipation helps plan future actions. Duration estimation aids coordination. Memory compression prevents overload. These mechanisms developed to help our ancestors survive, recognizing seasonal patterns, timing hunts, storing important experiences, while discarding routine ones. They just happen to create some odd side effects in modern life. Laboratory experiments reveal even more quirks. When shown successive images, your brain actually backdates your perception to when you first recognized a pattern. This creates an illusion that you perceived something before you actually did. Time perception isn't just about measuring duration. It's about constructing coherent narratives from sensory inputs. Age-related changes continue throughout life. Elderly individuals often recall recent events as happening just yesterday, when they occurred weeks prior. Meanwhile, childhood memories remain vividly placed in time. This shifting timescale reflects how memory systems evolve as we age. Recent, episodic memory weakens, while deeply encoded experiences persist. Neurological conditions demonstrate what happens when time perception breaks down. Parkinson's patients often underestimate time intervals. Schizophrenia can distort temporal sequencing. Migraines occasionally cause time warp sensations, where minutes feel like hours. These disorders reveal how fragile our timekeeping systems really are. Practical implications surround us. Retailers know products feel more valuable when customers spend time considering them. Hence long luxury shopping experiences. Theme parks design queues with distractions to make waits seem shorter. Video editors manipulate pacing to make films feel faster or slower than their runtime. Ultimately, your experience of time is a beautiful illusion, a construct woven from attention, emotion, memory, and biology. The next time minutes drag or years fly, remember, your brain isn't broken. It's just doing its evolutionary job of filtering reality into manageable chunks. Maybe time doesn't pass, we pass through it, leaving trails of memory that make some moments stretch while others vanish. This biological perspective explains personal time warps, But cultures perceive time differently, too. Some societies don't even view it as something that flows forward. Time across cultures. In English, we often talk about time as something can spend, save, or waste. You might say, "I don't have time," like you'd say, "I don't have money." This isn't how all languages work. Some cultures see time completely differently. The Hopi language doesn't treat time as something that moves forward in a straight line. Instead, they think of it more like a landscape, where things happen in certain conditions. This shapes how speakers understand past and future events. When English speakers imagine time, we usually picture the future in front of us and the past behind. But for the Aymara people in South America, it's reversed. Their word for tomorrow literally means the day behind us. When they talk about the future, they gesture behind their backs. For them, the past is what's in front because it's already known and visible, like scenery before your eyes. Different cultures organize their days based on different priorities. In many Western countries, people follow schedules strictly. Being late might seem rude, but in places like Latin America or the Middle East, time is more flexible. Meetings might start later than planned because relationships matter more than strict timing. These are called polychronic cultures, where many things happen at once rather than in sequence. Languages divide time differently too. Some have no separate future tense. Mandarin Chinese uses the same verb forms for present and future, adding words like tomorrow to show when something happens. This might make future events feel more connected to the present. The Piraha people of Brazil have no words for numbers or specific times. They live mostly in the present moment, without tracking exact hours or dates. Agricultural societies often see time as circular, following seasons that repeat each year. The ancient Mayans tracked complex calendar cycles spanning thousands of years. Their timekeeping connected earthly events to celestial patterns. Meanwhile, industrial cultures tend to view time as a straight line moving from past to future, useful for tracking progress and deadlines. How we talk about time affects how we experience it. English phrases like "back in the day" or "looking forward" show how we spatialize time. Swedish has two words for time: tid for clock time and gång for experience duration. German distinguishes between Zeit, abstract time, and Mal, specific moments. These subtle differences shape how speakers perceive temporal relationships. Cultural time orientations affect memory too. Studies show Westerners recall events linearly, while some Asian cultures remember in contextual clusters. Americans might list historical events in order, while Chinese participants often group them by themes or relationships. This suggests different mental frameworks for organizing time. Some languages mark time through landscape features rather than clocks. The Australian Aboriginal languages often tie events to environmental changes, when the wattle blooms rather than in September. The Inuit track seasons by ice conditions and animal migrations. These systems embed time within natural cycles rather than artificial measurements. Business practices reveal cultural time differences. German and Swiss companies value punctuality highly, while Brazilian or Saudi Arabian meetings may start late without concern. Americans see deadlines as firm, while Asians might view them as flexible guidelines. These attitudes stem from deeper conceptions about time's nature and importance. Religions influence time perceptions differently. Christianity's linear timeline contrasts with Buddhism's cyclical rebirths. Hinduism's vast cosmic cycles dwarf human lifetimes. Jewish tradition sanctifies weekly Sabbath time, regardless of productivity. These belief systems create distinct relationships with temporality. Even simple concepts like waiting vary across cultures. For Americans, waiting often feels like wasted time, but in Mexico, the verb esperar means both to wait and to hope, suggesting a more positive framing. Arabic has multiple words for different types of waiting, showing nuanced understandings. Children learn time concepts differently based on language. English-speaking kids master clock time early. Hopi children understand event sequences without linear framing. Mandarin learners grasp durations without tense markers. These early lessons shape lifelong time perception. Urbanization changes time relationships too. City dwellers follow artificial schedules disconnected from daylight. Rural farmers rise with the sun regardless of clocks. Nomadic cultures move according to resource availability rather than calendars. Our environments train us to experience time differently. Metaphors reveal cultural priorities. English calls time money, to be spent wisely. Spanish describes anger as burning time. Greek equates time with flowing rivers. These figures of speech unconsciously shape attitudes toward temporality in daily life. Festivals and holidays mark time culturally. The Western New Year counts forward linearly. Chinese New Year cycles through zodiac animals. Muslim months follow lunar phases. These celebrations reinforce different temporal understandings through ritual. Technology alters time perception globally. Digital clocks teach precise time consciousness, unlike sundials' gradual movement. Internet speed makes waiting more frustrating. Constant connectivity blurs work-life boundaries. Modern tools reshape ancient time relationships. Some languages grammatically distinguish witnessed versus reported past events. This forces speakers to consider how they know about past times. Others mark whether events occurred earlier or later in the same day. Such features create sophisticated temporal awareness beyond simple past-present-future. Body language reflects time conceptions too. Americans might gesture forward when discussing futures. Malagasy speakers gesture upward for past, like rising memories, and down for future. These physical metaphors demonstrate how deeply time orientation gets embodied. Historical trauma affects communities' time sense too. Groups suffering oppression often measure time through significant events rather than dates. Phrases like "before the war" or "when the rains failed" organize collective memory differently than calendars do. Age affects time metaphors differently across cultures. Westerners may see life as climbing, then descending a hill. Taiwanese Chinese often visualize life as descending through layers. Babies are higher, closer to ancestors, and elders lower, closer to earthly conclusion. These models shape how different ages value time. Tourists often experience culture shock around time norms. Mediterranean siestas disrupt Northerners' work schedules. Japanese train punctuality astounds visitors from more relaxed cultures. These encounters reveal how fundamentally time expectations vary. Climate influences time perceptions too. Equatorial cultures often lack strict schedules, since daylight hardly varies. Northern latitudes develop precise timekeeping to maximize short winters. Some African languages name hours by shadow lengths rather than fixed numbers. Industrialized nations share standardized time grids now, but underlying differences remain. A Japanese executive and Brazilian farmer may use the same clock, but experience time's meaning differently. Surface globalization hasn't erased deep temporal diversity. Ultimately, these variations show that time isn't one universal experience, but many culturally shaped perceptions. Your mother tongue and upbringing built invisible frameworks that filter temporal reality. Recognizing these differences helps understand why others might approach time unlike you. These cultural constructions layer atop biological rhythms we all share. Every human body contains internal clocks that tick regardless of language or tradition. But first, let's understand how these physical timekeepers work beneath our cultural perceptions. Your body's clock. Your cells keep time better than most watches. Deep in your brain, a tiny region called the suprachiasmatic nucleus acts as the body's master clock. This small cluster of about 20,000 nerve cells sits right above where your optic nerves cross. It tracks daylight through special cells in your eyes that detect light, even in people who are blind. Every morning, when light hits your eyes, this clock resets itself, coordinating thousands of biological processes that follow a roughly 24-hour cycle. These circadian rhythms control more than just sleep. Your body temperature rises and falls on this schedule. Hormone levels change throughout the day. Even your digestion speed varies by time. Nearly every organ has its own internal clock that syncs with the master clock. Liver cells know when to process food. Skin cells know when to repair themselves. Your immune system follows daily patterns too, which helps explain why flu symptoms often feel worse at night. Modern life plays havoc with these natural rhythms. Electric lights trick your brain into thinking it's still daytime after sunset. Screens make this worse. The blue light from phones and computers mimics sunlight especially well. When you check your phone in bed, that light hits your eyes and tells your brain to delay sleep hormones. Night shift workers face even bigger challenges. Their bodies keep trying to follow daylight patterns despite working overnight, which explains why shift workers have higher risks for health problems. Jet lag shows what happens when your internal clocks get confused. Fly across several time zones, and suddenly your brain thinks it's morning, while your stomach thinks it's dinner time. Some parts of your body adjust faster than others. Your sleep cycle might adapt in a few days, while digestion could take a week. This mismatch causes the fatigue and grogginess of jet lag. Older people often feel it more strongly because circadian rhythms become less flexible with age. Your chronotype determines whether you're a morning lark, night owl, or somewhere in between. These preferences aren't just habits, they're wired into your genes. Some people have genetic variants that make melatonin rise earlier in the evening, making mornings easier. Others have genes that delay melatonin release, making nights more alert. Teenagers naturally shift toward owl patterns during puberty, which explains why high schoolers struggle with early classes. Most people start shifting back toward lark tendencies after age 20. Light exposure determines how these clocks run. Bright morning light makes larks feel most alert, while owls often don't get enough evening light to properly shift later. Studies show office workers with windows get more daylight exposure and sleep better than those without. Even dim lights at night matter. A hallway nightlight might seem harmless, but can slightly disrupt sleep quality over time. Simple adjustments like morning walks or evening lamp choices can help align your schedule. These rhythms affect more than just sleep timing. Your reaction times are quickest during peak alertness hours. Memory works better at certain times of day. Even athletic performance follows a circadian pattern. Olympic swimmers actually swim faster in the afternoon than morning, regardless of practice times. Some heart medications work better when taken at night, while chemotherapy side effects vary by treatment timing. This field of chronopharmacology studies how drug effectiveness changes with body clocks. Your internal clocks developed through evolution. Early humans needed to be active during daylight and rest at night. Hormone cycles matched this pattern. Cortisol rises before dawn to prepare for waking, while melatonin increases after sunset to promote sleep. Even without alarms, most people naturally wake up when their elevated cortisol crosses a threshold. Animals show similar patterns, from nocturnal mice to birds that migrate by celestial cues. These rhythms exist in plants too. Flowers open at certain hours, and some trees release pollen on daily schedules. Modern schedules often conflict with natural timing. Early school start times work against teenage sleep patterns. Late-night work shifts force people to be alert during normal sleep hours. Even weekend sleep-ins can cause mild social jet lag when people return to early weekday schedules. The conflict between biological and social time helps explain widespread sleep deprivation in industrialized societies. Some workplaces have started adjusting for this. Hospitals letting night shift workers nap. Companies offering flexible start times for different chronotypes. Your body keeps time through complex interactions between genes and environment. Certain genes switch on and off throughout the day, controlling the production of proteins that affect cell function. Light resets these patterns through special photosensitive cells in the eyes that connect directly to the suprachiasmatic nucleus. Without light cues, human circadian rhythms gradually drift to about 24.2 hours, which is why blind people often have sleep difficulties unless given timed melatonin.
Simple changes can help sync your clocks. Morning sunlight exposure tells your brain the day has started, while dimming lights in the evening signals approaching sleep time. Keeping consistent meal times helps reset peripheral clocks in organs like the liver. Avoiding late-night meals lets digestion follow its natural nighttime downtime. Even exercise timing matters. Morning workouts tend to shift rhythms earlier, while evening exercise can delay them slightly. These small adjustments become more important with age as circadian rhythms naturally weaken. Ancient cultures intuitively understood biological timekeeping, though without knowing the mechanisms. Early Greek physicians noticed fever patterns followed daily cycles. Traditional Chinese medicine schedules treatments according to energy flows at different hours. Ayurvedic medicine in India connects daily habits to natural schedules long before modern science confirmed these connections. The sundials people once used to track sunlight hours actually matched how our biology tracks time better than mechanical clocks do. The precision of these biological clocks is remarkable. Without any external cues, humans can maintain sleep-wake cycles within minutes of 24 hours. Temperature and hormone fluctuations keep near perfect time, even without daylight. This precision highlights how deeply timekeeping is embedded in our biology at both large-scale rhythms and microscopic cellular processes. Each cell contains clock genes that cycle protein production on schedule, synchronized throughout the body by the master clock.
Sundials to atomic clocks. The earliest clocks cast long shadows across the sand. Ancient Egyptians around 1500 BCE built tall obelisks that worked like giant sundials. They watched how the shadows moved to divide daylight into parts. But these shadow hours weren't equal. Summer days had longer hours than winter ones. Still, it helped organize their days for farming and religious ceremonies. The moving sun gave everyone a shared sense of time before clocks existed. Water clocks offered the first way to measure time at night. Water would drip from one container to another at a steady pace. The Greeks and Chinese made more complex versions with gears and bells. Some could chime the hours automatically. These were among the first machines humans built that didn't need constant watching. You could say they were the earliest alarm clocks, too. The Maya civilization created impressive calendars without metal tools or wheels. Their long count calendar tracked time over thousands of years by watching the stars and planets. They could predict eclipses and planetary movements with surprising accuracy. These calendars weren't just practical. They connected Maya life to cosmic cycles in ways modern calendars rarely do. European monasteries needed better timekeeping for prayer schedules. The first mechanical clocks appeared in church towers during the Middle Ages. These early clocks didn't have faces or hands. They just rang bells on the hour. The sound carried across towns, reminding people when to work, pray, or sleep. It was the beginning of shared community time that didn't depend on the sun's position. Clockmaking took a leap forward in the 14th century with the verge escapement. This clever mechanism controlled how gears moved, making clocks more reliable. Now, clocks could be built smaller than church towers. Townspeople could afford clocks for their homes, though they still needed regular winding. Timekeeping was shifting from public to private use. Pendulum clocks changed everything in 1656 when Christian Huygens invented them. The steady swing of a pendulum kept time within about a minute per day, far better than earlier clocks. Suddenly, scientists could time experiments accurately. Towns could coordinate activities precisely. The pendulum's predictable rhythm made time feel more regular and controllable. Sailors faced a deadly problem. They couldn't tell how far east or west they traveled. Without knowing the time back home, ships got lost at sea. The British government offered a huge prize for anyone who could solve this. John Harrison, a carpenter with no formal training, spent years building marine chronometers. His final design, the H4, kept nearly perfect time even on rocking ships. Sailors could finally pinpoint their location using accurate timekeeping.
Traditional timekeeping methods still influence us today. The word clockwise comes from how sundial shadows move in the northern hemisphere. The 60-minute hour originates from ancient Babylonian math. Even our 24-hour day dates back to Egyptian astronomers. These systems stuck because they divided time into useful chunks long before mechanical clocks existed. The Industrial Revolution demanded precise time coordination. Factories needed workers to start shifts together. Trains required synchronized schedules to avoid crashes. Pocket watches became essential tools rather than luxury items. Time became something to save, spend, or waste, an idea that would shape modern life profoundly. Electricity changed timekeeping again. Electrically powered clocks could run for years without winding. Time signals transmitted by radio let people sync their clocks nationally. Suddenly, your watch could match clocks hundreds of miles away. Standard time zones replaced local sun time, making activities across regions align, perfectly developed in the 1920s. Kept time to within seconds per month. They used quartz crystals that vibrate at a steady frequency when electricity passes through. This principle powers most watches and clocks today. That ticking second hand isn't mechanical. It's counting millions of tiny quartz vibrations. Atomic clocks brought unprecedented precision in the 1950s. They don't measure mechanical movements, but count vibrations of atoms like cesium. A cesium atom oscillates exactly 9.192,631,770 times per second. That's now the official definition of a second. Modern atomic clocks won't lose a second in 100 million years. This extreme accuracy enables technologies like GPS, where a tiny timing error could mean being miles off course. These ultra-precise clocks reveal something odd. Time actually runs slightly differently depending on altitude. Einstein predicted this. Clocks tick faster on mountains than at sea level because gravity affects time's flow. Atomic clocks are sensitive enough to measure this. Your head technically ages faster than your feet,
though the difference is unimaginably small. Today's timekeeping relies on about 400 atomic clocks worldwide that average their measurements. The International Bureau of Weights and Standards combines these to define Coordinated Universal Time, UTC. Your phone syncs to this standard through radio signals or internet connections. We've come from sundials to atomic precision without most people noticing the change. The history of timekeeping shows our shifting relationship with time itself. Early clocks reflected natural cycles. Mechanical clocks let humans control daily rhythms. Digital time made every moment measurable. Now, atomic clocks reveal time as something far stranger than our ancestors imagined. Not just a measurement, but a dimension that bends and twists. These technological changes altered how we experience time psychologically. Ancient people might have felt time as cycles of light and dark. Mechanical clocks introduced the idea of uniform, divisible hours. Digital displays made time constantly visible in precise numbers. Each step made time feel more rigid and external. Rather than something flowing naturally, modern time, precision creates strange new challenges. Computer networks need clocks synchronized within milliseconds for financial transactions. Spacecraft require clocks that account for relativistic time dilation. GPS satellites must adjust for time moving faster in orbit than on Earth. Our daily lives now depend on timekeeping so precise, its effects concern Einstein's physics. Yet, for all this precision, time remains mysterious in fundamental ways. We can measure intervals with incredible accuracy, but still argue about time's true nature. The evolution from sundials to atomic clocks hasn't answered why we experience time's flow at all. Perhaps that's the next frontier. Understanding not just how to measure time, but what time actually is. This journey through timekeeping prepares us for Isaac Newton's view of time as an absolute background to the universe. He imagined time flowing evenly everywhere, like an invisible river carrying all events equally. This idea dominated science for centuries, until a patent clerk named Albert Einstein noticed something odd about light and motion, but that's a story for another moment. For now, consider how profoundly our tools for measuring time have shaped human civilization. From obelisks tracking shadows to atoms vibrating in vacuum chambers. Each advancement didn't just give us more accurate clocks, but changed how we think about time itself. Newton's absolute time. For over 200 years, scientists pictured time as an unchanging river that flowed at the same steady pace everywhere in the universe. Isaac Newton proposed this idea of absolute time in the late 1600s, and it became the foundation of classical physics. He described it as absolute, true, and mathematical time, of itself and from its own nature, flows equably without regard to anything external. That elegant phrase captures his vision. Time as a constant background against which all events occurred. This concept made intuitive sense. When you drop a ball, it falls to the ground at the same speed. Whether you're standing still or moving, the time it takes doesn't change based on your motion. Newton realized this principle applied universally. Whether you're on Earth, Mars, or floating in space, 1 second should equal 1 second everywhere. This assumption let scientists sync events across distances and make precise calculations about motion. Newton's absolute time worked beautifully for describing everyday motions. Calculating how long a cannonball would stay in the air, predicting when tides would come in, determining a pendulum's swing, all relied on this steady, universal flow of time. It became the invisible clock that kept the universe's rhythms. Scientists treated time as an independent variable that never changed its nature, regardless of circumstances. The success of Newton's physics reinforced this view. His laws of motion predicted planetary orbits with incredible accuracy. When astronomers discovered Neptune by calculating its gravitational effects on Uranus, It seemed to confirm time as this absolute background. The motions of celestial bodies appeared to obey Newton's equations perfectly when viewed through this framework. For solving practical problems about objects in motion, absolute time served science well for centuries. This idea shaped how people thought about measuring time, too. If time flowed at a constant rate everywhere, then making more accurate clocks simply meant building better devices to track this universal flow. The development of pendulum clocks, marine chronometers, and later quartz watches all aimed to measure this absolute time more precisely. People assumed these clocks revealed some fundamental truth about time itself, rather than just tracking local measurements. Absolute time became embedded in language and culture. Phrases like universal time and the march of time reflected this worldview. People spoke of time as if it were an independent force moving forward at a predetermined pace that nothing could alter. This way of thinking worked so well that few questioned whether time might be more complicated than Newton had described. Scientific measurements relied heavily on Newton's model. When explorers needed to determine longitude at sea, they used accurate clocks to compare local time with a reference time like Greenwich Mean Time. This worked because everyone assumed time flowed identically between the ship and the home port. The entire system of time zones that organizes our world today grew from this understanding of time as absolute and universal. Industrialization reinforced these ideas further. Factory whistles blew at set times, train schedules required precise coordination, and punch clocks regulated workers' days. The mechanical regularity of machines made the steady tick of Newtonian time feel like physical reality. People began structuring their lives around this artificial precision rather than natural rhythms of daylight and seasons. Yet, cracks in this model began appearing in the 1800s. Experiments with electricity and magnetism produced puzzling results regarding light's behavior. Scientists discovered that the speed of light seemed to stay constant regardless of the observer's motion. This contradicted Newton's laws, which suggested that if you move toward a light source, its light should appear faster due to your motion, just as a baseball thrown from a moving train would have extra speed from the train's motion. The Michelson-Morley experiment in 1887 demonstrated this problem clearly. They tried to measure changes in light speed caused by Earth's movement through space, but found no difference, no matter which direction they looked. This null result baffled physicists, who expected it to reveal Earth's motion through the hypothetical ether that supposedly carried light waves. If light speed stayed constant while Earth moved, something had to be wrong with Newton's framework. Other problems accumulated. Astronomers noticed Mercury's orbit didn't quite match Newton's predictions. The planet's elliptical path around the Sun rotated slightly faster than calculations suggested. This small discrepancy, called the precession of Mercury's perihelion, bothered scientists because Newton's theories worked so perfectly for other planets. These anomalies suggested that, while absolute time explained much about the universe, it might not tell the whole story. Some scientists tried to save Newton's model by proposing adjustments that would account for these oddities. They suggested possible properties of the ether or modifications to equations. But these fixes felt increasingly awkward as more evidence mounted that the problems ran deeper. The steady, universal flow of absolute time might not be as absolute as everyone assumed. Enter Albert Einstein, a young patent clerk who thought deeply about these problems. He realized that if light's speed was truly constant for all observers, as experiments suggested, then other things must bend to accommodate that fact. Time itself might need to be flexible rather than absolute. Where Newton saw a rigid backdrop, Einstein began imagining a more dynamic fabric, where time and space interacted. This didn't mean Newton was completely wrong. His laws still work perfectly for everyday speeds and scales. When you're calculating how long it takes a car to stop, or how a satellite orbits Earth, Newton's absolute time gives answers that match reality closely enough for practical purposes. The problems only appear
when dealing with things moving near light speed or in extremely strong gravitational fields. The shift from absolute to relative time didn't happen instantly. Many scientists resisted abandoning Newton's elegant framework, especially since it had served them so well for centuries. But evidence kept accumulating that, at cosmic scales or atomic dimensions, time behaved strangely. The steady flow Newton described seemed to be more like the surface of a river where currents and eddies create local variations in speed. Einstein's breakthrough came when he realized that time and space must be connected rather than separate. If light's speed remains constant regardless of motion, then time must adjust itself to maintain that constancy. A clock in motion must tick differently than one at rest. What seems simultaneous to one observer might not appear so to another moving at a different speed. This relativity of simultaneity shattered the notion of universal time. The implications were staggering. If time wasn't absolute, then the universe lacked a master clock, keeping everything synchronized. Your now might not align perfectly with someone else's now if you're moving relative to each other. Newton's timeless stage on which the universe played out became instead a dynamic, mutable fabric where space and time intertwined. This was no small adjustment. It required rethinking the very nature of reality. This revolution in physics began with those small cracks in Newton's model: the consistent speed of light, the odd orbit of Mercury, the failure to detect Earth's motion through ether. These anomalies that seemed like problems to solve within the old framework actually pointed toward a new understanding. Time wasn't the steadfast river Newton envisioned, but something far more interesting and complex. As we'll see, Einstein's relativity would reveal time as flexible, personal, and deeply connected to space in ways that still challenge our intuition today. But that's a story for the next section, when we explore how one patent clerk rewrote our understanding of the universe.
Einstein's time revolution. In 1905, a quiet patent clerk in Switzerland quietly changed how we understand time forever. Albert Einstein wasn't famous yet when he published his theory of special relativity, but his ideas would eventually turn Newton's absolute time on its head. Where Newton saw time as a steady river flowing at the same rate for everyone, Einstein realized time actually flows differently depending on how you're moving. This started when Einstein thought deeply about light. Scientists had discovered something strange. Light speed always measured the same, no matter how fast you were moving toward or away from it. If you're in a spaceship going half light speed and turn on a flashlight, the light still beams away from you at full light speed, not half. This shouldn't happen, according to Newton's physics. Einstein took this odd fact seriously and followed where it led. The solution meant time itself had to be flexible. Einstein proposed that time slows down for objects in motion relative to someone at rest. This effect, called time dilation, means a clock moving fast ticks slower than a stationary one. The faster you go, the more noticeable this becomes. At everyday speeds like cars or planes, the difference is too tiny to notice, but approach light speed and time slows dramatically. For someone watching a spaceship zoom past at nearly light speed, the ship's clock would appear to crawl. This isn't just theory, we've measured it. In 1971, scientists flew extremely accurate atomic clocks on airplanes while keeping identical clocks on the ground. After flying around the world, the traveling clocks showed slightly less time had passed for them. The difference matched Einstein's predictions exactly. Even at airplane speeds, which are slow compared to light speed, the effect was detectable with precise enough clocks. Time dilation gets stronger the closer to light speed you get. If you could travel at 87% light speed, 1 year for you would equal 2 years for people back on Earth. At 99.5% light speed, that stretch becomes 10 to 1. The famous twin paradox imagines one twin zooming off at near light speed while the other stays home. Upon returning, the spacefaring twin would be younger than their Earthbound sibling. Their biological clocks actually ticked slower during the journey, but speed isn't the only thing that warps time. Einstein later expanded his ideas into general relativity, where gravity also affects time's flow. The more gravity pulls at you, the slower time passes. This means clocks tick slightly faster on mountains than at sea level, where Earth's gravity is stronger. The difference is minuscule but measurable, about 30 seconds per year between sea level and the top of Mount Everest. Black holes demonstrate gravity's extreme effect on time. Near a black hole's intense gravity, time slows dramatically compared to farther away. To someone watching from a safe distance, a clock falling toward a black hole would appear to tick slower and slower, eventually freezing at the event horizon. For the person falling in, time would feel normal, but they'd see the outside universe speed up impossibly fast as they crossed the threshold. We actually account for relativity every day without realizing it. GPS satellites orbit about 12,550 miles above Earth, moving at thousands of miles per hour. Both effects come into play. Their high speed makes satellite clocks run slower by about 7 microseconds per day relative to Earth, while Earth's weaker gravity up there makes them run about 45 microseconds faster per day. The net effect means GPS clocks gain about 38 microseconds daily compared to ground clocks. Without correcting for this, GPS locations would be off by about 6 miles per day, getting worse continuously. Einstein's revelations show time isn't universal but personal. Your experience of it depends on where you are and how you move. Imagine space-time as a stretchy fabric where both motion and mass create ripples that affect time's flow. Two people might age differently if one travels faster or experiences stronger gravity. This flexibility seems strange because we never move fast enough in daily life to notice the effects. But at cosmic speeds or near huge masses, time bends noticeably. The implications challenge common sense. Events that appear simultaneous to one observer might not for another, moving relative to the first. Your now only perfectly aligns with someone else's if you're not moving relative to each other. There's no universal present moment. Time gets sliced differently depending on perspective. This relativity of simultaneity means the universe lacks an overarching now that applies to everyone everywhere. Interestingly, nothing can actually reach light speed from our perspective, because time would stop entirely for that object relative to us. As objects accelerate closer to light speed, the energy required approaches infinity because time slows so much for them. This prevents anything with mass from ever hitting light speed in our reference frame. Light itself always moves at light speed in a vacuum, experiencing no time passage at all from its own perspective. A photon's emission and absorption happen simultaneously from its viewpoint. Einstein's ideas also reveal that time and space are deeply connected. We shouldn't think of them as separate, but as a unified space-time, where what we call time depends on how we slice this four-dimensional continuum. Different observers might disagree on timing and distances between events, but will agree on the space-time intervals between them. This four-dimensional view treats the entire timeline of locations and events as existing simultaneously from a perspective outside space-time. This doesn't mean Newton was wrong. His laws still approximate reality well for typical Earth conditions. When building bridges or predicting planetary motions at normal speeds, Newton's absolute time works fine. The relativistic effects only become significant near light speed or extreme gravity. So for everyday life, Newton's view suffices, but the universe at large plays by Einstein's rules. The mathematics behind relativity uses transformations showing how distances and times convert between reference frames. These Lorentz transformations mix space and time coordinates between observers moving relative to each other. They preserve certain quantities like the space-time interval between events, regardless of perspective. This mathematical framework has been verified experimentally countless times. One surprising consequence is length contraction. Objects moving near light speed appear shortened along their direction of motion to a stationary observer. Time dilation and length contraction are two sides of the same coin, ensuring that all observers measure light speed as constant. These effects maintain causality, preventing time travel paradoxes by keeping cause and effect in order, regardless of perspective. Black holes provide extreme examples of relativity's predictions. Near their event horizons, gravitational time dilation becomes so strong that time appears frozen to distant observers. This leads to interesting thought experiments about what someone falling in might observe versus someone watching from afar. The reality likely involves quantum effects we don't fully understand yet. Einstein's relativity merged previously separate concepts of space and time into a single space-time fabric that can bend and ripple. Massive objects dent this fabric, creating what we experience as gravity. Moving objects follow straight paths, geodesics, through curved space-time. This geometric view sees gravity not as a force, but as the curvature of space-time itself. The warping of space-time propagates as gravitational waves, another prediction confirmed recently by LIGO's detection of ripples from colliding black holes. These waves travel at light speed, carrying information about violent cosmic events across the universe. Events like these give us new ways to test relativity's bizarre predictions under extreme conditions. Looking ahead, reconciling relativity with quantum mechanics remains physics' biggest challenge. Relativity describes time smoothly flowing at large scales, while quantum mechanics treats time as a background parameter without dynamics. Finding a quantum theory of gravity might require rethinking time's fundamental nature again. Some theories suggest time emerges from more basic building blocks at the smallest scales. For now, Einstein's revolution stands as one of science's greatest achievements, showing time isn't absolute, but relative, not separate from space, but woven with it into a flexible fabric. This understanding powers technologies like GPS while reshaping our cosmic perspective. Time isn't imposed on the universe, but arises from relations between events and observers. Your experience of time's steady ticking is really an approximation that works because we don't move too fast or experience extreme gravity. Under different conditions, time's flexibility becomes obvious. Next time you glance at a clock, remember, it's measuring something far more interesting than Newton imagined. Not universal ticks, but your particular slice through space-time's intricate geometry. This warping of time leads naturally to another mystery: why time only seems to move forward. From relativity's perspective, space-time just exists. Your experience of time's flow isn't built into the equations. That puzzling directionality connects to thermodynamics and entropy, which we'll explore next as we consider why you can remember yesterday, but not tomorrow. Like fragments floating to the surface, some pieces of time's puzzle are starting to connect, while others remain stubbornly mysterious.